All right, 9-5 symmetry. Let's do this. All right. 9-5 symmetry. There we are. All right. Line symmetry. This is a reflection. And so an example of that might be if I have kind of this sideways chevron. If I look at this and I try to find the line of symmetry, it'd be right here. That's the line that my shape could be folded, and it would be one, it would be a mirror image of itself right along this line. So let's see if we can, we'll draw some examples here. So on your homework you might see something that says draw this shape and show where that has symmetry, if there's line symmetry or not. So we're going to do some examples of that. So here's one. So first we're going to draw a crab, and the way we're going to draw a crab is we're going to draw this somewhat kind of an ellipse here, and then another kind of ellipse or part of an ellipse off the top of it. And then we're going to draw some legs coming out like this on that side, and some legs on this side. And then the crab's eyes would be like right over here. And then the crab needs to have some big claws. And then another big claw. Now, does this crab have symmetry? And so it wouldn't be this way, but look, if you draw a line right here, you can fold that crab in half, and if we were to draw this, perfectly, then it would have line symmetry right here. Let's look at another one. How about a starfish? So a starfish looks something like this. We'll have a 5. Well, how about we'll draw like kind of like, there we go. Let's draw like a star, I guess. There's a starfish. Okay, now, or a star. Now, for a star, if I were to draw a line right here, you can see that this side is a mirror image of this side, so this has symmetry here. Also, if I were to draw this better, and I draw a line right there, this side would be a reflection of this side. Same with this one, from here to here, and this one from here to here. So this has 1, 2, 3, 4, 5 lines of symmetry. Oh, did I miss one? Here we go. So yes, this crab has symmetry, line symmetry. Yes, this starfish has line symmetry. Now, what about this like conch shell here? So this looks like this. Here is a shell. This one is all bumpy and stuff. It has this something on this side and this on this side. This guy doesn't have line symmetry. I can't draw a line here to make one side the same as the other side. So this one, no, doesn't have line symmetry. Now, you try. So the way we're going to do this is we're going to do these examples. You're going to pause the video after I'm done, or when I tell you, and you're going to try to decide if these have line symmetry or not. and then you'll unpause, and we'll see what you got and how you did. Okay. All right, so we have these three shapes. We've got this parallelogram. We've got this five-sided object here, and we've got this rectangle. So you are to decide, does this have line symmetry, and draw the lines. Okay, so go ahead and pause. All right, welcome back. Let's see which of these shapes has line symmetry, and let's draw the lines. So let's look at A here. I can't fold this in half and make it symmetrical. I can't make it a reflection. So this one is no. And maybe I'll do a little example of that in a second. This one, if I draw a line here and fold it in half, then that's not symmetrical. But I can draw a line this way and fold it in half, and each side is a mirror image of one another. So yes, this one has line symmetry, and it's right there in the middle. Now, this rectangle is symmetrical this way, right down the middle. It's also symmetrical this way, right across the middle. Now, some of you might say, oh, it's symmetrical this way as well, but it is not. So what if I were to take this piece of paper here, which is a rectangle, right? Rectangle, piece of paper. I can fold it in half, and that is a mirror image of itself. I can fold it in half like this. It's a mirror image of itself. Now, if I try to fold it from corner to corner, there's no way to get this piece of paper to fold perfectly on top of itself from corner to corner. And you can try that at home. Just get a piece of paper, see if you can do it. If you can, let me know. We have to change the way math works. All right, so same thing with this parallelogram here. That would not work either. So if you had a piece of paper that was in the shape of a parallelogram, that wouldn't work unless it was a diamond. A diamond is a parallelogram. That one would have line symmetry, and that would be okay. All right, let's do some more symmetry. So that's line symmetry. Now we have another type of symmetry, and that's called rotational symmetry. So rotational symmetry means like it can be rotated to map onto itself. So let's see what that means here. So let's say I have a square, and right here in the middle of the square, this is my center of symmetry. So there's my center of symmetry in that square. And if I was to rotate this square 45 degrees, then it would turn to be right here like this. Right? 45 degrees from there to there. So if I rotate it 45 degrees, it's not mapping onto itself. It's not in the same orientation as it was before. But if I were to take it from here and I were to rotate it 90 degrees, there's 90 degrees, then it does map on itself. So notice how this shape is in the same orientation as this shape. So there it is. So let's talk about a couple words that we need to know, some vocabulary here. So order is the number of times the figure maps onto itself from 0 to 360 degrees. So remember, 360 degrees is all the way around once. The magnitude is the smallest angle for first map. And the way we see that is we say 360 degrees over whatever the order number is. That's how we can find what the magnitude is. So let's look at this. Let's do an example here. So for the square, the order is 4. So the square will map onto itself 4 times from 0 to 360 degrees. The magnitude is 90 degrees. So as we saw here, we had to turn it 90 degrees in order to get it map onto itself again. So, and then if we were to do that 90 degrees once, twice, 3 times, 4 times, it would go all the way around 360 degrees. All right. It'd be awesome if we could have some interaction here and I could help explain some stuff, but hopefully this will work. Okay, so let's do some examples. So if I have if I have a hexagon that is regular, meaning all the sides are the same length and all of the angles are the same measure. So first I have to decide, does this have rotational symmetry? And then I need to know what the order is. And I need to know the magnitude. So the order is how many times it maps onto itself from 0 to 360 degrees. So if I start here and I were to turn it one bit until it maps onto itself again, it would map onto itself once, twice, 3, 4, 5, 6 times. So the magnitude is 360 divided by 6, which is 60 degrees. So I would turn this 60 degrees in order to get it to map onto itself again. All right, let's look at another one. Let's look at this triangle. So rotation, does this have rotational symmetry? Can I turn it in such a way that it maps onto itself again? So if I were thinking about turning it, there's nothing I can do to this one. So this is no, this doesn't have rotational symmetry. So there's no order and there's no magnitude. How about this shape? Kind of like a flag shape. All right, so now does this one have rotational symmetry? And if it does, what is the order and what is the magnitude? Let's think about that for a second. So this shape, if I were to turn it 180 degrees, if I was just to rotate it 180 degrees, it would map onto itself. So yes, this does have rotational symmetry. And the order would be 2, because I would 180 degrees, boom, once, and then another 180 degrees, that'll get me to 360. So the order is 2. And the magnitude is 360 divided by 2, because my order is 2. 360 divided by 2, which is 180 degrees. All right, let's do one more. Let's do a star. Okay, this should be like a perfect star, right? Okay, so does this have rotational symmetry? If I take a star, turn it, it should map onto itself as I turn it. So yes, it does have rotational symmetry. The order and the magnitude. So if I start here, let's start right here. If I turn it once, it maps onto itself here. Turn it again to here. That's 2, 3, 4, 5 times. And then the magnitude would be 360 divided by 5. 360 divided by 5 is 72 degrees. All right, and so that is rotational symmetry. We got one more thing to look at for symmetry, and that'll be it for 9-5. The last part of rotational of symmetry here is three-dimensional symmetries. Okay, three-dimensional symmetries, here we go. We've got plane symmetry. Which is a reflection. And so let's draw what that might look like. So I'm going to draw a like a parallelogram here like this. And then I'm going to draw a line straight down, a line segment straight down from each vertex. Then I'm going to connect each of those. And so now I have this rectangular prism here. So this is a three-dimensional object. Now, if I were to slice this in half with a plane, so here's my plane, kind of like a piece of paper. And I were to slice this thing in half, so I'm going to go halfway from here to here, and I'm just going to draw a dotted line to signify that my plane has crossed right through here, right in the middle. You can see how this side is a mirror image of this side of the rectangular prism. I've cut it right in half, and now this one side is a mirror image of the other one, so therefore I have plane symmetry right here. If I was to look at this from a top angle, from the top view, it would just be a rectangle with a line through it, right? And so this side would be a mirror image of this side. And so what we've done here is we've just brought it to 3 dimensions so you can see it from a different angle. So that's plane symmetry. Now the other type of three-dimensional symmetry is axis symmetry. So axis symmetry is a rotation. So let's look at an example of what that might look like. So I'm going to draw an ellipse or sphere like that, and then I'm going to draw like a triangle on top of it going to the right. And I'm going to draw a little point right here in the middle of this sphere, or this ellipse. And then I'm going to draw a dotted line that goes from the vertex to that dot, and through that dot I'm going to just draw an arrow. So I've drawn a line that goes through this cone. So we've drawn a cone, and I draw a line that goes through the center of this cone. And I can rotate this on that center line, and this will continually map onto itself. So this has rotational symmetry, where if I turn it, however much I turn it, it's going to map on itself. Now let's see, let's do two examples here. We're going to decide what kind of symmetry does this have. What type of symmetry? So we're going to draw two shapes, and then we'll talk about the symmetry. So we're going to draw kind of a backwards kind of L shape, fat L shape. And then off of each of these vertices, we're going to draw a little line that's going back at like 45 degrees, little line segment. And then we're going to connect each one of those. And we have this shape. And now we're going to draw another shape, and then we're going to talk about what kind of symmetry these have. And so now I'm going to draw a perfect five-sided object, a regular pentagon. And then straight down from each of these vertices, I'm going to draw a line segment that is equal length from the other ones. And now I'm going to draw what looks like what is happening on the back of this that we can't see here. So I have a pentagonal prism, and I have this crazy shape here. So what kind of symmetry do these shapes have? Let's look at this one first. If I cut it this way, I've got no symmetry here. If I cut it this way, I've got no symmetry. But if I were to take a plane and cut it right in half here, all the way across, and so I have this shape that's kind of a sandwich, and I go like this. If I were to cut it in half, I would see that I have symmetry, plane symmetry. So this one has plane symmetry. Because if I were to cut it in half here, all the way around with a plane, then this half, the back half, would be the same as the front half. Symmetry. Now this one, this shape, I could cut right down the center of it with a plane, and I would have two perfect halves, two halves that are a perfect reflection of one another. And I could do that 5 different ways. Right? I could cut it this way, I could cut it this way. So I could have 5 planes. So this does have plane symmetry. I could also cut it in half this way. I could cut straight in the middle of it, and then I would have 2 halves that are perfect. So that has plane symmetry. Now this also, if I were to put a dot in the center of it, it could rotate onto itself just like the star did. That we looked at. So I could rotate it just like I rotated the star 5 times, and it would have an order of 5 there. So this has plane symmetry and rotational symmetry. Plane symmetry and rotational symmetry. All right, and that is it for 9-5 symmetry.